Now, so this is one thing that we need to take care of. Now, let's briefly discuss what are the different design methods that we have for two-way slabs. Okay, and the first method is the simplest method, which is called chord coefficient method, which is given in your Annex D. Okay, so in Annex D, it is given, which is called as chord coefficient method. Now, this is most important thing. This method is applicable only for slabs that are resting on walls or very stiff beams. So you take each panel. If the panel is resting on only very stiff beams or walls, then actually you can isolate this slab and do analysis. And this, in fact, this is an extension of elastic analysis of slabs. Okay, and this is based on Rankine-Grashof method. And here, what we have really done is highly indeterminate two-way slab is idealized to a determinate system. Okay, and the moments have been derived. Okay, with certain assumptions. Okay, so here, what is that we do is in both the directions. For example, in this direction, bending, what we do is we convert the slab into edge strips like this and then middle strip. So what are the dimensions of your edge strip? If it is spanning on this Lx and the width is Ly, the width of the edge strip is going to be Ly by 8 and Ly by 8 here and Ly by 8 here. The remaining distance is going to be 3 Ly by 4. That is what we are going to call that as a middle strip. Okay. Then the coefficients, moment coefficients will be given for what are the positive moments and negative moments on these strips. Now, what are the coefficients of moment is actually expressed as alpha x times W, where W is your load, usually in kilonewton per meter square, that from your loading requirement that you take, IS 875 part 1 and part 2 will give you an idea what kind of loads that we need to consider in our analysis. So we take the load is given to you, and spans are usually fixed based on the architectural requirements. So Lx and Ly will be given to you, right? And the thickness of the slab usually we calculate based on your L by D ratios, which we will discuss about that. Right, just like for beams and one-way slabs, for two-way slabs also, the thickness is usually governed by deflection criteria, and you have some thumb rules, L by D ratios that we need to satisfy. So Lx and Ly will be given, depth will be given, and load is given. So I need to find out what are the moments that I need to design, or in other words, how much reinforcement that I should put should come from my analysis. Basically, what we are really doing here is an analysis, and for the slab panel, depending upon the boundary condition that you have, we are discretizing them into edge strip and middle strip in both directions, and then we are finding out the moment values based on these coefficients, which are your alpha x and alpha y. So the moment along x direction is going to be alpha x times w times Lx square, and moment along y direction is going to be alpha y times w times Lx square. Now, what are this alpha x and alpha y? These are the coefficients that have been derived based on elastic analysis and based on this Rankine-Grashof method, and the code is giving you some values. Okay, and W is your total design load per unit area, and Mx and My are the moments on strips of unit width spanning Lx and Ly respectively, and Lx and Ly are the length of the shorter span and longer span. So Lx is always taken as a shorter span, and Ly is always taken as the longer span. So now let us look at what are the different boundary conditions that you will have. So again, this method is applicable only for slab panels that are resting on very stiff beams or stiff walls. Then only I can isolate the wall and do the analysis. Otherwise, if it is sitting on a flexible beam or a flexible wall, there is going to be an interaction between the slab panel and the supporting elements. So I cannot really isolate the slab and do the analysis. So this method is applicable only for slabs that are resting on very stiff beams and stiff walls. Okay, now let us look at it. Depending upon where the panel is located, you can have 9 different boundary conditions. Okay, the red color, what we is written is it's a continuous edge or a fixed edge. The blue color is actually a simply supported edge. So now you can have very first case. Now all the 4 sides of the panel can be continuous. That means I can have slab continuous on all 4 directions. That means on the continuous edge, I'm going to develop some negative moments, right? So in a support, because of the continuity, we know that it's going to develop some negative moment, right? Now we can also have another condition that only three sides are continuous. This is an edge of the building. Okay, let's say edge of building. That means, okay, this is the edge, the outermost line of the building. The slab is not continuous on one side, but on all the three sides, it is continuous. Then you can have the same thing on the longer edge will become discontinuous, but all the shorter edge can be continuous. Similarly, what I can have? I can have two sides which are continuous, and these two edges are discontinuous. Okay, these are discontinuous edges. Okay, now we can also have two longer sides continuous and then two shorter sides discontinuous. That is also possible. Like this, you can have different boundary conditions. Again, you end up with this last case. All the four sides are simply supported or discontinuous. So, depending upon the support conditions and the type of the slab, that is edge restrained or simply supported, the moment coefficients can be obtained from table 26 and 27 of the code. Now let's look at table 26. So what does the table 26 says? Okay, these are your bending moment coefficients. So using these coefficients, we got the moment. Now basically you have depth is known, width is known, and all we're doing is a sectional analysis. So it's very straightforward. So the major task in this method is actually to find out what are the moments at different locations. Okay, so that is the thing. So now let us look at the code. Again, it is based on elastic analysis and it is also from Rankine-Grashof method. The highly indeterminate system has been converted into a determinate system, and these coefficients have been derived. Okay, and again, this method can be applicable only for slabs that are resting on very stiff beams. Okay, you cannot really use this for systems, either flat slabs or flat plate. You cannot use this method. Similarly, if you have a very shallow beam which is very flexible, then also you cannot use this method. Okay, you have to keep this in mind. Now, if you see here in this table, we have different cases that are there. So the 9 boundary conditions that we have discussed in the previous slides, those are listed here. That's starting from interior panel. So interior panel means all the four uh, edges will be continuous. That means that it is the interior part of the building, and on all four sides the slab is being continuous. So in this case, depending upon what is the ratio of your longer to shorter span, Ly by Lx, these alpha x coefficients is given. These are called as short span coefficients. Similarly, for all values of Ly by Lx, anyway, in the longer directions, as we have seen, the moment variations are not going to be that much. Okay, and that is the reason the code is giving you simplified one value, which is alpha y, and there also, if you look at it, the long span coefficient, you will have only one value. Okay, it is going to be independent of Ly by Lx. Okay, so if you see here, so what is the short span coefficient? Let's look at it. If your Ly by Lx is, let's say, equal to 2, okay, then negative moment is going to be 0.065, alpha x is 0.065. Similarly, what is the positive moment at midspan? It is 0.049. These are the moments that I need to use for interior panel for when the ratio of Ly by Lx is equal to 2. Okay, so these are the panel. Similarly, what would be the long span direction? Negative moment is going to be 0.032, alpha y is 0.032, and for positive moment I take 0.024. Right, so I get moment distribution in both the directions like this. Okay, one at support, for example, right, 0.065 for shorter direction for negative moment, 0.049 for positive moment at midspan for in the shorter direction. Okay, so for example, if you take this panel, okay, in this case, let's say this your panel. So this is your shorter direction and this is your longer direction, right? So in this case, I'm going to use alpha x. In this case, I'm going to use alpha y. Of course, in the alpha x and alpha y, you have two values are given depending upon whether you're looking at the negative moment or positive moment, right? So that's similarly for other boundary conditions are also there. For example, let's look at the last case. Four edges are discontinuous. That means the slab panel is actually simply supported. There is no continuity, and all the four edges are not continuous. It's a simply supported slab panel. And this is again short span moment alpha x for different Ly by Lx. Now, if you look at it, when Ly by Lx for in this case is equal to 2, okay, so what happens? You have only positive moment. Similarly, on the long span also alpha y in this case, this is alpha y, right? This is also positively. Why? Because the edges are discontinuous, I'm not going to develop any negative moment. That is why I'm getting only positive moments. Okay, only but alpha x is going to change as a function of it Ly by Lx. So here Ly by Lx is changing, and this is it for value of 2. Okay, so depending upon the aspect ratio of the slab panel, your moment coefficients are given. So the moment coefficients, once you find out, you again each panel is discretized as right, middle strip and edge strip, and then you distribute these moments whatever that you got, okay, as per the code provisions. That's all. It's a very simple method, and the coefficients are directly given to you, so you can use it and you can distribute it in edge strip and middle strip accordingly in both the directions, short direction as well as in the long direction. Now let us look at what are the minimum thicknesses of two-way slabs to control the deflection. Okay, so we have studied for beams and one-way slabs what are the L by D ratios. So the code is actually saying for flat slabs. Okay, these provisions are given for flat slabs in general. For slabs that are sitting on beams, okay, the code is not really very comprehensive in giving the guideline. In that regard, we would be either using the ACE code provisions or Canadian code provisions, which we will discuss. And these observations are made for actually flat slabs. Okay, so what the code is saying is that 31.21 it recommends that L by D ratios prescribed in 23.2, which we will see for the structural members in general, can be adopted for flat slabs with some differences. Now, what are the differences? The longer spans should be considered for flat slabs, okay, instead of shorter spans in one-way continuous beams, or unlike the case of slabs that are supporting on walls or strip beams where the shorter span is considered. For flat slab, we should always consider longer span in these LBD ratio equations, which we will see. Now, when you are providing drop panel in a flat slab, as per 31.22, which again we'll discuss that, if it is not provided around the column supports, then again for flat slab, the LBD ratio should be further reduced by a factor of 0.9. So that means what? First cases we will see. Whatever the LBD ratio that is given in 23.2, there you have to use longer span. Okay, that is first condition when you apply to flat slabs. Next condition is if you do not have drop panels properly given with the minimum dimensions specified in this class 31.22, then you are not going to have a very stiff system. Then what is the code is saying is whatever the ratios that are given, that again you reduce it by factor of 0.9 so that you will put more thickness of the slab. Okay, and for a flat slab again, minimum thickness of the flat slab should be at least 125. For any slabs, in fact, I would strongly recommend you put at least 125. Okay. Okay, so now we talked about those L by D ratios. Now let us see what are those L by D ratios. Okay, so this is applicable for one-way systems. Okay, for beams and slabs that we talked about. But the code is saying that even for flat slabs, you can use this. Okay, that's what the code is saying. And let us look at it. So we have seen that in beams, for basic values of span to effective ratio, up to 10 meter. Okay, for cantilever, LBD ratio should be 7. For simply supported beam, it is 20. For a continuous system, it is 26. So again, for a one-way slab system or one-way beam system, your end span, one side will be continuous, one side will be simply supported, right? And the interior spans will be both sides continuous. So you have to do this LBD ratios and provide thicknesses or depth, which is satisfying the most stringent condition. right? So you have to use this values. Okay. Now again for these are again it is for one-way system either be the same, but this is applicable for two-way slabs also, especially for flat slab. That's what the code is saying. 31.21. Okay, it is saying that whatever prescribed in 23.2 is can be used for flat slab with some changes. Okay, only thing longer span I need to use, and the drop panels if they are not conforming to the minimum dimensions that are specified, which again we'll discuss that, then again this ratios you need to multiply by zero point 0.9. Okay, further reduced. So if I reduce the LBD ratio, obviously my thickness or the depth requirement will go up, right? Right. So now let's look at it. These are for beams. So this can be applicable for flat slabs, and you have to use longer span in L. Okay. Now we have also seen that there are some modification factors. In fact, in deflection calculation, deflection module, we have discussed it. What are those deflection modification factors? Depending upon how much is your tension steel, I can have modification factor ranging from zero point 0.8 to as high as 2. If I put lot of steel on the tension side, my stress in the tension steel is going to be less for a particular service moment. If the stress is going to be less, the strain is going to be less. If strain is less, the curvature is going to be less. If curvature is less, the deflections are going to be less. So that is the idea. To put more than what is adequate for service moment tensile stress, and then code is basically helping you to relax the tail by D ratio requirement. Okay, that's the modification factor for your tension steel. And then we also looked at another modification factor for compression steel. So again, why is the compression steel plays a role? We have seen that that is going to help in tackling the creep induced deflection, long term deflection. Similarly, it is going to help in controlling the shrinkage, right? So both the shrinkage induced deflection and creep induced deflections will reduce significantly if you put good amount of compression steel. So that is the reason the code is saying that depending upon the percentage of compression steel, you can again modify by some factor which is modification factor for your compression steel. Okay. So with multiplying. So that's why these ratios are higher than 1. Okay. So you can go for a larger L by D ratio. When you have a larger L by D ratio, your depth requirement will come down. Right. But however, for tension steel, it starts from 0.8 to 2. Sometimes if you are putting less steel also, the code is penalizing. If you are putting more steel, then code is rewarding. So in the tension steel, the values modification factor can range from zero point 0.8 to 2. But for compression steel, it is always more than 1. Okay. So these are the things. So for flat slabs, we use the same values. Again, instead of shorter span, we are going to use longer span. And then we have to use this modification factor as well. Okay. And these are the changes. Now for drop panels. Okay. For drop panels, now if you look at it, the code gives you guideline that your drop panel when you're providing to a flat slab, it should satisfy some minimum dimensions requirements. What are those minimum dimensions requirements? Let's say if my span for this flat slab is LX1 in one direction, okay, and LY in the other direction, right? What the code is saying is if you take this, let's say this interior panel, okay. So what we are saying here is this is basically your capital, okay. This shaded color is capital, right? And this color is your drop. Okay, so column it becomes capital and then it becomes a drop. Okay, so that's why drop panel is, when you look at it in the plan, a drop panel is going to have a larger area, then capital is going to have a small area, then the this is your column right in the middle, right? This is the way it is. What the code is saying is whatever the dimensions of the slab drop panel that what we provide, let's say from center line, if I take this as x1 and x2, right? So let's say this is x1 and x2. This x1 and x2 should satisfy some minimum dimensions. And what are those minimum dimensions? This x1, which is if I take the span as lx1, it should be greater than or equal to lx1 by 6. That means the center line on one side, center line span divided by 6. If I take that value, whatever that projection that I have given here, this x1 should be greater than Lx1 by 6. Similarly, x2 also, now I have to take, because I'm talking about this span, right? So I have to take Lx2. So x2 has to be greater than or equal to Lx2 by 6. In the same way, y1 has to be greater than or equal to Ly1 by 6. Y2 has to be greater than or equal to Ly2 by 6. So these are the minimum dimensions the drop panel should have. Okay. Now, why is that minimum dimensions? Okay, anyway, provision of drop panel will help in reducing the punching shear stress. It will stiffen the area around the column, and it will also help in reducing the deflections. All these things are fine. But why the code is giving you the minimum dimensions is, now instead of the thickness of the slab, for example, let's say this is your slab thickness. So when I look at elevation, so this is slab, this is your drop, right? This is your column, right? Now, if you look at it, this thickness is, let's say, h, and this is your thickness of the total thickness, let's say h1 and h2. H2 is going to be definitely greater than h1, because now we are also including thickness of the drop panel. Now, if I put this minimum dimensions of the drop panel in my moment resisting capacity calculations at the support regions, instead of taking this H1 depth in my calculations, I can take H2, provided I satisfy this X1 and Y1 dimensions for the slab. Okay. So because why is it in around the column supports where I'm going to put reinforcement? I'm going to put reinforcement at the top, right? So let's say now in this case, wherever I'm going to put reinforcement, my reinforcement is going to be like this. Okay. Now what would be the effective depth for the maximum span? So it is going to be this. Okay, this is your effective depth. So if my slab drop panel is also considered in my moment resisting calculation, my effective depth increases like anything, right? It increases by the magnitude of the thickness of the drop panel, right? So then you end up good savings in your negative moment reinforcement. But to take advantage of that, you have to make sure that this x1 and y1 are going to satisfy the minimum dimension requirements that are specified. Then only you can take advantage of this. Otherwise, the effective depth or the depth for your moment resisting calculation, you should take only the depth of the slab. If you want to take larger depth in your calculations, then we need to provide minimum dimensions of slab drop panels in the planned directions. Now, one more thing. Now, column capital also. So, column capital also, we slightly, if your load requirements are high and if the span is getting higher, only drop panel is not helping. Then again, you put some slight capital on the top of the column like this. So, you provide this kind of a capital. Okay, so this is what, sorry, not this. We have actually put this column capital is going like this. Okay, now in this capital, now I say you can put whatever may be the dimension of the capital. What the code is saying is, in your punching shear calculations and other things, code is saying that now if I put one cone, right circular cone inside that capital, whatever the dimension that is occupied by the code, that is what you have to take that as a useful part of capital to be used in your calculations. So what does it mean? So this red color is the actual capital that I have constructed. Now what the code is saying is, okay, let you go ahead and put, let's say, a right circular cone. So let's say this is the edge of the uh, column. So from this edge, if I draw a line like this, similarly at this edge, I am drawing a line like this. This is basically, we call that as a right circular cone. Why that we call that as a right circular cone? Because it has to maintain this 90 degrees. Okay. So whatever that maximum right circular cone that I can embed it within that capital, that is the useful dimension I can take. Okay, so that's what's it. So only that portion of the column capital lying within a pyramid or cone with vertex angle of 90 degree to be considered in the design calculations. So the code restricts the useful portion of the column capital to the portion which lies within the largest pyramid or right circular cone, which has a vertex angle of 90 degrees, that can be included entirely within the outlines of the column and the column head. So that is the effective portion of the column. So this is the, so though this may be this, so this actual red color is the one that we have provided, but the effective capital size is actually this. Okay, which is wrong. So that is your effective capital size. Though red color is what you have provided, but this violet color, right, is the one that is going to be useful part of your column capital. Okay, so again the code is saying that the critical section for calculating the factor negative moment should not be taken at a distance not greater than 0.7175 L1 from the central line of the column. Now, when you calculate your clears, this critical section for your negative moment, okay, you cannot take at a distance not greater than 0.175 L1 from the center line. So that means this is your center line of your column. This distance, whatever that you take, okay, so this cannot be, let's say this is your critical section. This cannot be greater than 0.175 L1, where L1 is your span in the direction where you are doing the calculation. Okay. So these are the provisions for drop panels and column capitals, especially when you have flat slab. These all the small changes also will make a difference. So that you have to be careful. Okay. So let's summarize what we have discussed in this module. We discussed different types of slabs based on the aspect ratio, and we discussed what is the difference between one-way and two-way slab actions. Right? It's not only based on your Ly by Lx dimension. Even for us, when your Ly by Lx is greater than 2, right, or less than 2, if you have support only on one direction, then it will predominantly bend in one direction. So it's not only based on your aspect ratio of the panel, it also based on how the slabs are supported will determine whether the slab is bending in one direction or two direction. And we also discussed why torsion comes into picture in two-way slabs, right? We have discussed to tackle the torsion, especially when the corners are prevented from lifting up, you need to put mat of reinforcement in the corners at the top and bottom to avoid significant cracking. And then we also talked about different types of slab systems. And then we discussed code coefficient method, okay, for two-way slabs. Okay, this is the first method, simplest method. Again, this method is applicable only for slabs that are resting on very stiff beams or walls. Okay, now what is stiff beam or flexible beam? We will discuss in the next coming parts of the module. I think these are some of the useful references that you can see. And again, I would like to thank my PhD student, Mr. Mohan Krishna, for helping me with preparation of the slides. Thank you. We'll see you in the next module.